When it comes to selecting an inverter and battery storage for a solar installation, it can sometimes be confusing deciding what inverter is going to be best for the size of the system and which batteries are going to offer the customer the maximum amount of output without breaking the bank. In our previous video, we designed a solar array system for our 4-bedroom property, which gave us a peak generation of 4.5 kilowatts, which made the property 23% independent from the grid. In this video, we're going to be selecting an inverter and battery for our 4-bedroom property and looking at some of the factors which may affect our decision when selecting the equipment. And if you didn't know, this video is one in a series of videos that we have made in association with SunSync on the installation of a solar system. They can be viewed individually, or you can click the link in the description below to view them as part of a free online training package to help you with your CPD and receive a certificate when you've completed the course. Before we start looking at inverters and batteries, let's remind ourselves of the numbers we've worked out from our 4-bedroom installation. Our installation has an annual consumption of 4,382 kilowatt hour with an average daily use of 12 kilowatt hour. We managed to get our peak demand down to 6 kilowatts in the evening by moving some of our higher consuming appliances like the washing machine and dishwasher to come on in the day. We are looking to install a 10-panel system with an output of 4.5 kilowatt peak, and we estimate a total annual generation of 3,974 kilowatt hours with a self-consumption of 995 kilowatt hours. This makes our installation 23% independent from the grid. So now that we have the solar array planned out, we now need to select a suitable inverter for the installation. But with so many different inverters available and different sizes, it can sometimes be difficult to know if you're selecting the right one. So let's start with what an inverter does. A solar inverter is an electrical converter which changes the direct current or DC electricity captured by the solar panels into alternating current or AC, which is the standard flow of electricity required for electrical circuits and domestic appliances. The two types of inverters I'll be focusing on in this video is string inverters and hybrid inverters. So what are the differences? A string inverter in most cases will only take solar and convert that into AC for the installation. You can't charge batteries with a string inverter, so it is the simplest of inverters available. A hybrid inverter, on the other hand, can take that DC from the solar array, convert some of it to AC and send it into the installation. But it could also send some of the DC into the battery, so it can work across both AC and DC. This inverter is also bidirectional, meaning you can charge your battery from the DC solar array and also charge it from the AC side as well. What this means for our customer is that a hybrid inverter can manage the AC and DC inputs and outputs and send them to where they are needed at the right time. Inverters also come in lots of different sizes, with manufacturers offering lots of power output options. If we look at this range of hybrid inverters from SunSync, we can see that they start off with a 3.6 kilowatt hybrid inverter. This is useful for the UK market as it's compliant with G98 and can be installed without prior approval from the distribution network operator. Other sizes are 5.5 kilowatts, 8.8 kilowatts and a massive 16 kilowatt inverter. You can also get these range of inverters in 3 phases for industrial or commercial applications. So it may seem obvious that we would choose an inverter that matches the generation output of our solar array. So with our solar array being able to reach a peak of 4.5 kilowatts, then a 4.5 or a 5.5 kilowatt inverter like this one here may seem a logical choice, right? Well, this isn't always the case, as we're going to look at from our 4-bedroom installation, which has a 4.5 kilowatt peak solar array, and I'm going to be using this 3.6 kilowatt hybrid inverter. As we have seen from our installation, it is unlikely that a solar array will reach its peak generation. This is due to a number of factors: the time of the year, the orientation of your roof, the pitch, the weather. Even if it's too hot, the efficiency of the panels will decrease the hotter that they get. So a lot of factors have to be right for us to be able to achieve the peak generation. But let's take the scenario that our panels will achieve 4.5 kilowatt peak. We can show this on my chart here at the middle of the day when we hit our peak generation. But our inverter is 3.6 kilowatts, so how will it cope with this amount of generation? Well, this inverter from SunSync has a multiple power point tracking or MPPT input of 7 kilowatts, but only outputs into the installation at 3.6 kilowatts. This is to keep the unit within the G98 guidelines, and be sure to check out the video I did on G98, 99 and 100. But what about the remaining 3.4 kilowatts? Well, the inverter can divert that energy to battery storage, so none of it is wasted. Let's assume though, for our scenario, we don't have battery storage. What would happen to that energy above the 3.6 kilowatts? Well, the generation is clipped by the inverter, meaning the energy generated above the kilowatt output of the inverter is dissipated within the solar panels as heat. Now, it looks like we have lost nearly half the energy generated because our inverter is too small, but that's not the case. By calculating the areas of this chart, it turns out we've only lost about 18%. So we've had 82% of solid generation through our inverter. And even if we showed this chart again, but in the winter when the days are shorter and the sun is lower in the sky, we don't generate as much, but we still retain 92% of our generation. Even on a cloudy day where the generation falls below the 3.6 kilowatts of the inverter, we are retaining 100% of the panel generation. So the inverter does not affect the generation of the panels and has very little effect on the amount of energy which is being sent into the installation. Another consideration with inverters is their optimum efficiency performance. Inverters are never 100% efficient. That's because they need to take some power to run themselves, but they do run more efficiently the closer that they get to their maximum operating power limits. If we bring back our graph showing the generation in the summer and add some efficiency banding of the inverter, we can see that if we used our 3.6 kilowatt inverter, even though we have clipped some of the generation, we have doubled the amount of time the inverter is working at its most efficient. So that initial 82% could actually be a lot higher. And here is another thing. If you have an east and west orientated roof, then an oversized system is a perfect solution as the sun tracks across the sky. This is why most inverters have 2-string inputs to allow for this configuration. In the morning, your eastern array will begin to generate electricity, and as the day moves on, the western array will begin generating, and this can lengthen the time your panels are generating electricity. This creates a flattening effect, so having a large array on the east and west elevation can be worth it, not to mention that the inverter is in its highest efficiency band for longer. So what inverter is going to be suitable for our 4-bedroom installation? As we have a 4.5 kilowatt peak from our solar array, and it is unlikely to generate at its peak, but we still want an inverter to operate at its highest part of its efficiency band. So 3.6 kilowatt inverter does look good. And as our customer is wanting battery storage as well, then this 3.6 kilowatt hybrid inverter will be perfect for the job. So now we've selected our inverter, we now need to select a battery suitable for the installation, and for this we need to consider a number of factors. First, we need to decide what size batteries we need for this. We need to go back to our energy consumption graph that we saw in the first video. As we have an average usage for the day of 12 kilowatt hour, it would be ideal to have batteries which are able to meet that usage. However, costs and space may be a limitation. If I take 2 of these 5.32 kilowatt hour batteries, that will get me some way towards the average usage for the day, remembering also that we are only using more energy in the winter than in the summer. Next, we can look at the peak demands. Here we can see peaks as to where most electricity is being used, and thanks to some load shifting, we managed to move some of our consumption into the day. This is the instantaneous power of the property, and we can see that at periods it peaks towards 6 kilowatts. There are several factors which can determine the installation's ability to meet peak demand. Let's have a look at them. Firstly, the rating of the inverter. This is fundamentally the limit in which the energy will be released into the installation. Next is the amount of energy the batteries are able to discharge at, what we call the C rating, and I've done a Q&A video on this. Let's look at our consumption table. So if I wanted to be able to supply the peak demand of 6 kilowatts in the evening, then we will need to use an inverter capable of outputting that amount of power. We would also need to select batteries to meet that peak demand, as it's in the evening and the solar is not generating energy. This 5.32 kilowatt hour battery has a C rating of C0.5, meaning it can discharge half its energy over an hour, so 2.5 kilowatt. If I had more batteries, I then increase the amount it can discharge. So to meet the peak demand of 6 kilowatts, I would need 3 batteries. I would also need an inverter capable of delivering that much power at that time to meet the demand. All this equipment though will increase the cost of the installation, which may not benefit us, or it will take too long to pay back. Plus our inverter will be more than the solar array, meaning we won't benefit from oversizing the PV array. So it is a balancing act as to what size system the budget will allow and one that will yield the best return on investment. Either way, we can expect to have some reliance on the grid, but the amount will depend on how well the system is designed. If I take this 5.32 kilowatt hour battery, which can discharge 2.5 kilowatts, and add this to the graph, we can see here that the battery is able to manage some of the loads throughout the day. However, when the energy usage is at its peak, we will have to supplement some of that from the grid. We also need to think about charging our batteries and the best time for it. If we again look at our consumption chart and plot on a typical solar generation period, we can see that in the day we are generating more energy than what's being used by the property. So this is a perfect period to take that excess energy and divert it into battery storage. Even in the winter when generation is not at its highest and the energy generated is not enough for the household and we charge the batteries, we can utilise smart energy tariffs which will charge your batteries up when electricity is cheaper. So if you've not got a suitable roof for solar panels, it may be worth having a battery only system, as you can save money on peak energy tariffs by buying your energy cheap and using that energy when you need it. Another factor to consider with our battery selection is the state of charge, or SOC, and the depth of discharge. These two terms are the exact opposite of each other. If we look at the battery indicator here, we can see it's on a scale and it has a SOC of 60%. This is the usable capacity of the battery, and if the state of charge is 60%, it means we have a 60% energy available. The depth of discharge is the term normally used to indicate what the battery can be discharged to. So a 90% depth of discharge will discharge the battery to 10%. So let's get back to our installation and remind ourselves as to what we have selected so far. We are fitting a 10-panel array with a generation peak of 4.5 kilowatts. We are going to oversize our PV array and fit a 3.6 kilowatt hybrid inverter onto the system. And to manage the loads in the property throughout the day, we are going to install two 5.32 kilowatt hour DC coupled batteries. We can add these into our worked examples from our previous video to see what difference adding the battery storage has on our self-consumption. So if I bring back our chart and we look up our battery size in table 7.15, we can see that we get a self-consumption percentage of 81%. In reality, what that means is if we take our annual consumption for the year at 4,382 kilowatt hours, we offset that with our self-consumption of 3,219 kilowatt hours. And that gives us an estimated grid independence of 73%. We now have all the information we need to complete the pre-sale information on the MCS documentation to give to the customer. This will allow the customer to review all the cost-saving benefits and the initial outlay required for the system. In the next video, we'll be looking at where we can install all this equipment needed for the solar PV system. And if you want to learn more about solar and storage systems, then be sure to click the link in the description below to watch it as part of our free training package to help you with your CPD and receive a certificate as well. But until then, it's bye-bye for now.